So this is our module going through 2A repeated measures ANOVAs. Everyone's, yes, brains will be scrambled. Yay. Okay, our research scenario is kind of similar to our previous one. So a researcher was interested in discovering whether a short-term high-intensity exercise training program, so last example was a longer intervention. This one's a short-term exercise training program. And we want to see if that program significantly changes the CRP concentration. So in this particular example, we recruited 12 participants and had them perform 2 trials, a control trial and an intervention trial. We'll pause there because in the description, we now know we have 12 people who have been repeated 2 times so far. Control trial, intervention trial. So the type of trial or the type of exercise training program is one of our independent variables. I have a note added on that they had sufficient time between trials to allow for residual effects to dissipate. That way we know we're not kind of like cross-contaminating our effects. CRP concentration was measured 3 times at the beginning, midway, and at the end of the trial. So the time of collection is a similar example to our one-way ANOVA. Subjects continued their normal activities for the control trial, and then during the intervention trial, they exercised intensely for 45 minutes each day. So we're still interested between control and intervention, the effects of exercise, but we're also interested in the progression of change over time. So intervention, 2 levels, control versus intervention group, and then we have the levels of time based on how concentration levels change. So CRP concentration, still our dependent variable. If you don't like words, I also outlined it in a flowchart because flowcharts. We have independent variable A. In my example, I'm calling treatment. Independent variable B, we will call time. We already identified in the previous slide, we have 3 time points that we took CRP concentration measures at. And each person went through no exercise intervention as well as an exercise intervention. So when we decide what we want to call this test, 2 components we have to have. The number of independent variables is 1. So we could refer to it as a 2-way blah, blah, blah ANOVA. Or we can refer to it by the levels. So we can call it a 2x3 or a 3x2. I've seen this naming convention actually quite a bit in research, so it is something that is utilized. But these 2 things would identify the number of variables we have. And then the types of samples has to point to something that suggests we have repeated measures or within subject independent variables. So we can say a within or repeated measures. You could also write RM for any of these naming conventions. So I think on like the last exam, I would give you a research scenario and say, what kind of test would you run in this instance? If you put 2-way RM ANOVA, you still get full points. I just know repeated measures is kind of long to write. So anyways, we put all these together and we get a bunch of different possible namings that would be completely correct in any way you write them. Okay. So we have now figured out that we have 1, 2, 3 measurements per trial, which means that we should have 6 measurements total per subject. So when we go into SPSS, we need to make sure we have 6 columns to match each level of our variables or each level combination. So INT is representing our intervention or exercise group or treat trial. CON is our control trial. And then we have 1, 2, and 3 representing the time points for each trial. Again, all of our measures should be listed as scale, so that when we pop it into our data view, if we look at one subject, they have 1, 2, 3, 4, 5, 6 values or 6 CRP measurements that were taken, which is what we should have. Okay, so that's one way to make sure you set up your test right, is take the number of levels of one independent variable, multiply it by the levels of the other independent variable, and that should be how many columns you end up with in SPSS. So let's say this went swimmingly. We can now set up our test. Again, we're going to assume we have a normal distribution with no significant outliers for the dependent variable. The way we get to the test is exactly the same pathway as the one-way repeated measures. So analyze, general linear model, repeated measures. And then we define our variables similarly to last time. In this case, I had said I'm going to use the labels treatment, which we have 2 levels, control and intervention. We click add, pop it into our factor box. I'd do the same thing for time. So I'd put time in this box with 3 levels, click add, and then we get it in here. And then I can also add my measure name, which is CRP, or the dependent variable, and I add that in here. So the order does matter. And I do a good example of this in the activity this week. But what's going to happen is our variables are going to first be sorted by the treatment, and then they're going to be sorted by the time. So if there's a particular way that you have set up your data in SPSS, example being, if you look at this, we have our intervention groups lined up first, and then they are sorted by the time. Okay, so that's going to directly translate into what the data look like if you put your variables in this way. So once we define our levels, we then identify them in the repeated measures dialog box. So up in the top here, you can see in our parentheses, the code, or like the secret to the labels, is that the value that comes first in the parentheses is representing levels of treatment. So we have 3 measurements for each control group and intervention group. And then the second value in the parentheses is representing time points. The way that you insert these is very important. So keep it in your head. First one is treatment. So that would be identifying all of our, or grouping our intervention people, maybe with the label 1, and grouping our control people with the label of 2. And then each of our individual time points gets their own level for that second value in the parentheses. Luckily, these are kind of just set up so that they can pop right in. So then it would end up looking something like that. We then can set up our post hoc tests using our EM means button. And I just saw a question, so I'm going to pause for a second. Before inputting the variables into SPSS, would we have to reorganize the data on Excel in the same order? Sometimes it's helpful. Other times, like if you just want to organize data in Excel the way that makes sense to you, and then plug and chug your values individually, that works too. So it's easier when you can just clump or like select all of your variables and insert them at one time. But if it doesn't end up working out that way, then it's okay. As long as you're, putting your values in the correct spots in terms of how you defined your variables, you shouldn't have a problem. Okay, so we're setting up post hocs using our estimated marginal means. We can see we have a lovely little effect size, or interaction effect now. So we can put both the main effects for our independent variables and the interaction effect interaction effect into our display means for box, compare them with a Bonferroni adjustment, and continue. So this process is something that you've seen before. When we click the options button in the main repeated measures dialog box, we'll choose the same boxes that we did for the one-way ANOVA, so descriptive statistics, estimates of effect size. Click continue to get out of the options window. And then at the bottom of this here, remember last time when we had a two-way independent ANOVA, we had to change the syntax in order to get the pairwise comparisons added for the interaction effect. So we're going to do the same thing. So that's where the paste button lives. And there's butter. We click on paste, and then the syntax window will open. Initially, when you look at the syntax, it'll have EM means for treatment and time. And then there will also be a treatment times time, but there will be nothing after that. So we add the compare treatment with a Bonferroni adjustment, copy this line of code, paste it underneath, and then replace treatment with time. So the first kind of post hoc or pairwise comparisons that we're setting up is going to be investigating the differences between our control and our exercise group within the different pre, mid, and post time points. The second one we're setting up is going to be comparing pre, mid, and post time points within just the control people or within just the intervention exercise people. Technically, they're all the same people, but different trials. Okay. Once we have this set up, we can then go ahead and run all for the syntax, which will generate an output for us. And this is when we get to start checking our assumptions, which gets kind of wild. So when we have Mauchly's test, you're going to see each main effect or each independent variable in addition to the interaction effect. We have to check sphericity for every single one of these. So if it helps you guys, when I say report the p-value for sphericity, and you want to make a bullet list for treatment, time, and treatment times time, or independent variable A, independent variable B, interaction effect. That way you remember I have to check all three of these, okay? We're going to start off with the p-value for Mauchly's test for the treatment, which is a pretty easy one because there's only 2 levels. So control, intervention. When we only have 2 levels, we automatically assume sphericity. Woo! Okay. So again, the null hypothesis for sphericity is that we have basically equal variances of the differences between our treatment trials. So we're just going to say we accept the null hypothesis even though we don't have a p-value, and we assume sphericity. So that means when we get to our ANOVA table, under the treatment row, we're going to read the sphericity assumed row, okay? The next one we can check is for time. So we have a p-value here of 0.027, and that is less than 0.05. So that means we have rejected our null hypothesis and violated sphericity. Oh no. So when we violate sphericity, we look at the epsilon value in the greenhouse geyser box. That's this guy here. Okay. And then we say, is that value less than or equal to 0.75? In this case, it is. So we can determine that we're going to use the greenhouse geyser adjustment for the time variable when we read the main effect in the ANOVA. Okay. If, however, this value happened to have been greater than 0.75, we would have used the Hunefeld adjustment instead. There is a common misconception that I do want to point out while I'm thinking about it. some people think that, oh no, I violated sphericity. I have to look at the greenhouse geyser value. And when I say report the p-value for the assumption of sphericity, they end up putting the epsilon value. This is not a p-value. None of these values are p-values. The only p-values you will ever see in a table are always going to be under a column that's headed by the word sig. Okay, so when you report p-values for Matchley's test, you report the p-value in the sig column, write your interpretation, and then figure out what adjustment to use. Okay, so don't get ahead of yourself when you're writing your interpretations. So again, reiterating, sphericity was violated for time, so we read the greenhouse geyser row in the ANOVA table for the time section. Okay. The last thing we have to check for sphericity is our interaction effect. So in this one, we have a p-value of 0.072. That is greater than 0.05. Thus, we accept the null hypothesis. And we can say that we have met the assumption of sphericity, or our variances of the differences between our treatment trials or each time point are equal. Most of you guys in here are probably just going to say sphericity is assumed. It's so much easier. But if that's the case, we know we will read the sphericity assumed row for the ANOVA table. Okay. That kind of like rounds out checking our sphericity assumption. Does anyone have any questions before we move forward? Okay. So, assumptions, check. We now know which of our main effects met our assumption of sphericity and which ones violated. So now we can know how we need to interpret the ANOVA table. We'll start with the main effect of independent variable A. I keep coming back to this kind of task list. So if you ever get lost in the PowerPoints, these are your anchors, okay? But just to give you an idea, this is what the test of within subject effects table looks like. So it's really big. And in each slide, when I look at each of these main effects separate from one another, I cropped the table. So if you're looking at the examples and you're like, why isn't there a smaller table in SPSS? Why does it hate me? It actually looks like this, but I cropped it. So don't freak out. All right. As a recap on our assumption, we had said that our treatment, because it only had 2 levels, assumes sphericity. Our time violated sphericity, but we determined a greenhouse geyser adjustment was appropriate. And then our interaction effect also met our sphericity assumption. So these are what we're going to be going off of for the p-values for our main effects. And I think for Juan's question earlier, when we have multiple independent variables, you see the condition and the error row for each variable get stacked on top of each other. Thus, how we get 3 different F statistics and 3 different p-values. That was just a callback. Okay, so when we're looking at the main effect of treatment, we said sphericity was assumed. So we look at the p-value in that row. We would report it as p is equal to 0.002, less than 0.05, so we reject the null hypothesis. The main effect of treatment is telling us that there are no significant differences between the control and the intervention group, regardless of when our CRP concentrations were taken. So if we took all of our control measurements, pre, mid, and post, doesn't matter what grouping those were in, all of our control measurements, all of our intervention exercise measurements, took the means of those 2 groups and compared them to one another, we end up with a significant effect of the exercise intervention on CRP concentrations. So that's one way we could interpret that p-value. Because we do have a significant main effect, well, I just put a note down here, we need to go back to our post hocs to see where the differences lie. Technically, because there's only 2 levels of treatment, we already know that the differences are between control and intervention groups, but it's a good habit to have a schedule or like a process, okay? So that checks off main effect A, significant effect of treatment. Now we're going to see if we have a significant effect of when the measurements are taken. So that was our time independent variable. We determined greenhouse geyser adjustment was appropriate, so we look at the p-value in that greenhouse geyser row, and we have a p-value less than 0.001, significance. So we say that the time or time has an effect on CRP concentration, or the way I interpreted it down here, there's at least one significant difference in CRP concentrations between time points. So it could be that pre is significantly different from mid, pre is significantly different from post, or mid is significantly different from post. I don't know which pair is significant. They all could be significant. Who knows? But that's what the post hocs are for. Okay. So check off another main effect. We so far have a significant effect of treatment and a significant effect of time. Now we need to figure out if there is a significant interaction between treatment and time. So then we consult our interaction portion of our table. We assumed sphericity, so we can read the p-value in that row. And p would be reported as less than 0.001. Reject the null hypothesis because it's less than 0.05. So we have a significant interaction between the treatment and time. Treatment, you could also say, is the exercise intervention. Either way is fine. But again, significant interaction calls for post hoc tests or pairwise comparisons. So when we summarize all of these main effects together, we now know we have to check the pairwise comparisons for treatment, for time, for treatment within the levels of time, and for time within the levels of treatment. Okay, if any one of these, like any one of the main effects or the interaction effect, if any of those had p-values greater than 0.05, we can leave them out of the post hoc post hoc test pairwise comparisons. We don't have to look at them. But because all of them were less than 0.05, we do have to look at them. Okay. So we'll take a look at our pairwise comparisons for treatment first. Again, I mentioned it's not super necessary because we already know there's only one pair that can happen between 2 levels. So the p-value of 0.002 would indicate that CRP concentration in our control trial, well, actually that's 2, is significantly different from the CRP concentrations in our intervention or exercise trial. Okay. This is just my note on the 2-level thing. Okay. So that checks off our pairs or significant pairs for treatment. Control is significantly different from intervention. We then can look at the pairs for time. Let's take a look at that table. I show you guys, I actually think several of you, with the exception of 3, several of you guys were in office hours today, and I discovered such a cool thing. You can create highlights in your tables in SPSS. So I show you how to do that in the activity this week, and I wish I knew how to do it earlier, Because when there's so many p-values and like redundant pairs, highlighting, it makes it so much faster to read stuff. So this is looking at pre versus mid measurements, and we can see there is a significant difference between the pre and the mid CRP concentrations. We also have a significant difference between the pre and the post CRP concentrations. We can skip this one, 1 and 2, because we've already compared levels 1 and 2 together. And the next thing we can compare is levels 2 and 3, which is significant. So 1 and 2, 1 and 3, 2 and 3. 3 possible pairs when you have 3 levels of your independent variable. So one way that we could interpret these 3 significant pairs is that all time points resulted in significantly different CRP concentrations, regardless of the intervention trial being performed. So this is if we took everybody who had their P measurement. Doesn't matter if you were in control or if you were taking your measurement from your exercise trial. Everyone goes in one bunch. All of our mid values go in one bunch. All of our post values go in one bunch. And then we say, do we have significant differences and where are they? Clearly, all of the pairs were significantly different. So this now takes care of our pairwise comparisons for our main effect of time. The last pairwise comparisons and the hardest ones to go through are the interaction effects. So we'll first look at comparisons of our control and intervention. So if control and intervention are significantly different from each other within the pre, the mid, and the post measurements. That's what this one's looking at. So in our table, that's the thing. The other thing I found out today is you can change the labels in the table because repeated measures, because you have to put in, when you define your variables, you say, this is how many levels I have. I found out you can change this to like continuous and, or this is not continuous. This one's an intervention, continuous time being 1, 2, or 3. That one's fine. But sometimes when you have more and more levels and they just keep building on top of each other, it can be really difficult to keep your numbers straight. So I found out a way you can label actually pretty quickly in the table, and then it makes it easier to read. But when we consult our pairwise comparisons, we really only need to look at the top row of each comparison, because the treatments that we're comparing are the same in this row compared to this row, right? It's still control versus intervention trials. For our pre-measurements, we can see that our samples were not significantly different from each other, which is a good thing because that indicates that everybody started kind of at the same baseline point. And that's nice for proving if the intervention actually had an effect on CRP concentration. So in time point 2, midway through the intervention, we see a significant difference between our intervention and our control group, or control trials, same people. And then we also see we have a significant effect between our intervention and control trials for the post measurement, which was after 2 weeks. So when we put all of this information together, we have significant pairs of intervention and control for the mid-intervention time, that's here. And we have significant differences between intervention and control for the post-intervention time. So we could lump all this together, and our interpretation might sound something like CRP concentrations in the control trial were significantly different from the intervention trial for the mid and post-intervention measurements only. And that is that. Okay, so we've got one of our interaction pairwise comparisons down. We still have a fourth one. So that's when we're looking at differences between time points within our treatments. So looking at pre versus mid, pre versus post, mid versus post. all of those comparisons just in the control trial, and then all of those comparisons just in the treatment trial. We end up getting a table that looks like this, and I apologize it's on the small side, but if I blew it up, I wouldn't have room for my interpretations. So when we look at the table, we end up noticing that we have significant differences between pre and mid and pre and post measurements for the intervention group. And we also have a significant effect or significant difference between the mid and the post measurements. So those are our significant p-values. All the other ones I didn't highlight are redundant with the ones that are highlighted. And then the rest of these down at the bottom are not significantly different. Okay, so I feel like pairwise comparisons, or when you actually look at the interaction effect, it can be really nice because you see the progression and if people's concentrations are significantly changing over time. In the intervention group, which was treatment 1, we can actually see progress, right? In terms that their CRP concentrations are decreasing as time passes. Versus our control trials, CRP concentrations didn't really change. So looking at interaction effects like this kind of help to point out that exercise does actually play a role in CRP concentrations. So I've listed all of my pairs down here. All of them I just noted to you guys verbally. But we can interpret this as there are significant differences in CRP concentrations for all time points in the intervention trial, but no significant pairs in the control trial. And that is that. Okay. Any questions on pairwise comparisons? So that's the ending point of the ANOVA. After this, it's the effect sizes, which seem to be the other common point of confusion for most people in office hours today. And we're doing good on time. 10 minutes, we can finish. Super easy. Okay, if you have questions, put them in the chat. The last thing we're doing is looking at the effect sizes for each of our main effects. So again, we have 3 main effects, 1 for the independent variable of treatment, 1 for the independent variable of time, and then 1 for the interaction effect, which we kind of hold loosely because the effect size has to be looked at in the pairwise comparisons tables, or like deeper in that area of the output. So when we want to find the effect size of our independent variables, we consult our ANOVA table. This is the exactly same procedure that we did last week with independent ANOVAs. So for the effect size for treatment, I used the same row that I got my p-value from for the main effect. So because I assume sphericity for treatment, I'm going to use the partial eta-squared value in the treatment row. Now, for this example, all of our values are the same. It doesn't always turn out that way, so it is important to keep your rows tidy, okay? But in this case, we would say that the effect size for the differences between our control and intervention trials is large, okay? And I didn't really get into it a whole lot when we started looking at our partial eta squared, but this is actually a measure of variance, or describing the difference between means in terms of variance. So it's actually interpreted very similarly to R squared that we used in regressions. So even though we interpret these as small, medium, or large effect sizes, they can also be interpreted as like 60% of the variation that we see in CRP concentration can be attributed to a person exercising or not exercising. So anyways, that's our effect size for our main effect of treatment. We then can get the effect size for our main effect of time. also considered a large effect size based on our criteria in the table. And we would interpret that as there's a large effect size for the difference between time points, or differences between time points. For our interaction effect, it usually is underneath this portion of the table, but for interaction effects, we have to look elsewhere. So in our independent ANOVA examples, you guys had a univariate test sitting underneath the pairwise comparisons. In a repeated measures ANOVA, you're going to have pairwise comparisons and then a multivariate test table. So that's what this guy is. And we'll have p-values listed for each of our time points. Okay. Specifically, if you squint, you can see it at the bottom. This says that the simple effects, which are also pairwise comparisons of interaction effects, they're also referred to as simple effects. Okay, the simple effects of treatment within each level combination of the other, I think usually it's the effects shown. So we are really looking at the differences between treatment within each given time point. So for the pre-intervention value, we have 0.035. That is considered a small effect size for differences between the treatment trials for the pre-intervention measurement. You can use that same kind of template to phrase the interpretation for the rest of the effect sizes. Now on the activity, I will ask you guys only to list the pairs of the significant effects. So if you ended up having a significant main effect, you would list the effect size for that main effect. If you had a significant effect of your second independent variable, you list the effect size for that second independent variable. Again, both of those come from the test of within subjects effects table, which is your main ANOVA. If you had a significant interaction, this is where you go to your multivariate tests. And you can't just check one, you have to check two. So we've got one out of the way. The other one is going to end up telling us the simple effects of time within each level of our intervention groups or intervention trials. So we would interpret 0.820 as a large effect size for the differences between time points in the intervention trial, which is labeled 1. Our other effect size is 0.084, which I would probably consider medium to large, probably closer to the medium side. So we'll say we have a medium effect size for the differences between the time points in the control trial, because now that's what number 2 represents. Okay, did we make it? We made it! All right, brains are likely fried, but a lot of this really is repetition. So you have seen it before aside from sphericity, so hopefully it's not too overwhelming. You get more practice with your wording. I was already planning on grading activity 7 on the lenient side because easing your way into these is not always the easiest task. So if you guys are like, oh no, like wording, I suck at wording, I don't know how to interpret stuff, always go back to the PowerPoints. Okay, I think the SPSS PowerPoints, I give you guys enough examples of like how you can template your responses, that if you know what your independent variable is in your example, you know what your dependent variable is, you just plug them in to here.